Hi all, this is chapter 7.11, predicting products substitution versus elimination. Okay, so this is chapter 7.11. And the question is, let's say you're given a reaction like this. Where you're taking some alkyl iodide and you're reacting it with sodium methoxide, and you see the product looks like this. And the question is, how do you know what the mechanism is? Is it substitution or elimination? Well, here it's probably elimination because it's very difficult for there to be any substitution on a tert-butyl group here. But let's perhaps take a different example. There we are. And we're going to treat this with sodium hydroxide. How do you know what the product is of this reaction and if it is a substitution or elimination reaction? Because you can actually get 3 different products here. And each of them have to do with a different reaction mechanism. Because if you remember, this first one would be the result of an E2 elimination, as would the second product, but the third product would be a result of an SN2 reaction, a substitution. So again, how do we know? Well, I'm going to present to you a few easy steps to hopefully help you in figuring out what the mechanism of a certain reaction might be. So first, what we should do, determine the reagent function. That means figure out if the reagent is an acid, a base, a nucleophile, or an electrophile. Probably since it's substitution elimination chapters that we're dealing with this time, we'll be talking about nucleophiles or bases. So you should try and think about, is this reagent a strong base? Is it a strong nucleophile? Next, and this is the one that's not so easy, determine an expected mechanism. So this means once you find or you think you found what the reagent is, that is a strong base or a strong nucleophile, then you can try and determine the expected mechanism. For instance, a really strong nucleophile that is not a very good base, such as the cyanide ion, that is going to be a much better substitution reagent than it is a base. Likewise, something that is a relatively strong base, like lithium diisopropyl amide, or LDA, that is a very good base, but a very bad nucleophile. So with the cyanide anion, we could expect there to be a substitution reaction happen, but with the LDA, we could expect there to be an E2 reaction happen, an elimination. So knowing what the reagent functions as helps you determine the mechanism. And then last, the key thing is the third step, determine any regiochemistry that you have to be aware of, or regiochemical outcomes, as well as stereochemical outcomes. If you follow these 3 steps, you should be able to pretty efficiently figure out what your reaction should progress as. In other words, a substitution or elimination. So let's go back real fast to the first step we had, which was to determine reagent. Oh, there we spelled reagent wrong. Reagent function. So, like I said, is this a nucleophile? Electrophile? Or let's not do electrophile because we know it's substitutions. A base? If it's one of those, is it strong? Is it weak? These are all questions you need to know because, for instance, you have things like very strong non-nucleophilic bases. Oh, let's draw this correctly. This is called DBN. And this is a very strong non-nucleophilic base. And it's very strong because when it accepts a proton, when it performs a proton transfer reaction, what you have is this type of structure. I misdrew this one here. There we are. Okay. There we go. You have this structure where there's a positive charge on the nitrogen, but that positive charge is stabilized by resonance onto the other nitrogen to give you, oops. This nitrogen instead. Okay, so again, being able to tell what the reagent function is key. All right, now determining the expected mechanism. So if you look at, this is number 2, determine mechanism. So do we have a strong base, but a weak nucleophile? Then that might be an E2, because then there's no substitution that might happen. Do we have potentially a strong nucleophile, but a weak base? Then maybe that's going to be a nucleophilic substitution reaction. Do you have a strong nucleophile and base? Well, then it kind of depends. You probably have likely E2 because the E2 reaction is faster than the SN2 reaction, unless it's primary. So I'll write unless the substrate is primary. And then last, do you have a weak base and nucleophile? Then in that case, it's likely E1 because the eliminations are typically faster, and if the nucleophile isn't very good, then typically it will be E1 because substitutions are slower. Okay, and then lastly, we have the regiochemistry we have to think about and the stereochemistry. So we'll say regio and stereo outcomes. Okay, so we can kind of make a little table like they do in your book where you have SN2, E2, E1, and SN1. Okay, so if we're going to think about the regiochemical aspects, the SN2 regiochemistry is completely controlled by, let's do this in light blue, is completely controlled by the alpha carbon of the alkyl halide. Whereas the E2 regiochemistry basically makes the Zaitsev product, unless the base is very bulky. And E1 also makes the Zaitsev product. And the SN1 again is dependent on the alpha carbon because that's what it attacks. And the stereochemistry, there are also some stereochemical outcomes to remember as well. And those are that in SN2, you have inversion of configuration. In E2, it is trans-specific and stereoselective. Meaning you can only have cis elimination or a trans element or an anti, it has to be an anti-configuration to make the E2 reaction happen. In E1, it prefers to be trans over cis. And then in SN1, it's mostly racemic because of the planar nature of the carbocation. You can find these notes as I've written them and as we've talked about them in the exam 3 notes module in your Canvas shell. So that's all, and I hope you all have a good day. Thank you.